Hello, everyone. Welcome to Silence is Not Golden, Disrupting the Load Balancing of Authoritative DNS Servers. I'm Fenglu Zhang, a PhD student from Tsinghua University. DNS provides critical services for the internet. As a result, DNS specification requires deploying load balancing mechanisms on authoritative servers. For example, RFC 1034 requires each DNS zoom should maintain at least 2 authoritative servers. RFC 2182 further requires this nameserver to be geographically and topologically diverse. Nowadays, DNS hosting in cloud service is becoming more and more popular. Such services provide infrastructures to support the resolution of hosted domains. More importantly, they simplify the complex work for customer to manage a domain. However, due to the consideration of cost, assigning different authoritative server for each hosted domain is impossible. Instead, many hosted domains share the same set of authoritative servers. Consequently, load balancing is critical to the stability and security of DNS hosting services. The outage of DNS hosting services can affect numerous domains. In this study, we review a new attack, disabilities, which can efficiently disrupt load balancing mechanisms of a kind of non-compliant authoritative DNS servers. Our comprehensive measurement proved the extensive target could be affected by this attack. Several mean-trained recursive DNS software are exploitable. A considerable proportion of popular domains are vulnerable. Also, we observed that attacker could exploit numerous open resolver and several public DNS services. The security impact can be served once an attacker disrupts DNS load balancing. An attacker can bypass existing defense mechanisms and overload nameservers. Note that such overload is different from most traditional DOS attack. The attacker direct legitimate DNS traffic to a victim instead of generating malicious traffic. As a result, the choice remaining for victim are increasing hardware capabilities or ignoring traffic from billion clients. Also, the attack can lower the bar of traffic hijacking and cache poisoning. The load balancing mechanism provides multiple candidate nameservers, which can be deployed on different location or AS. Disrupting the load balancing eliminates the probability for client to query diverse nameservers. As a result, manipulation of DNS response becomes less challenging. Moreover, an attacker can also disrupt the infrastructure of DNS-based load balancing systems. Some implementations directly configure each nameserver to respond with different size or a different set of resources. Therefore, an attacker against the DNS load balancing can subsequently impact the application servers assigned by nameserver. Now, let's move to the disabilities attack. We observed a prevalent response strategy of authoritative server. Silence is golden. In particular, they are configured to not respond to the DNS request outside their authority, while receiving a request for a domain outside of their authority. It slightly drops the request instead of returning any answer, such as refused or annexed domain. Its operator believes this is a good strategy against DNS application attacks. However, it's also a strategy violating the DNS specification. Failing to respond at all is always incorrect, regardless of the configuration of the server. Worse, such strategy of authoritative server can cause misunderstanding when a resolver meets a silent authoritative server. This is because the mainstream recursive DNS software prefer the nameserver with the best performance and avoid the nameserver failing to respond. Moreover, the status of nameserver is globally shared by all domains. Here is an example. We assumed that an attacker asked the resolver to query an authoritative server for the domain that is not hosted on the authoritative server. The authoritative server slightly drops the request and doesn't generate any response. Then the resolver considers the authoritative server is down and record the status for the authoritative server. Note that all domains globally share the status of nameserver. The next time, even a user query for a hosted domain to the resolver, the resolver will avoid querying the field nameserver and query other candidates. Such implementation caused the disobedience attack. Let me detail the attack with an example. We assume the victim's configuration is this. The DNS hosting services assign its hosted domain to NS records, NS1 and NS2.com. Each NS records point to 2 sites of authoritative servers. In total, 4 sites of authoritative servers are assigned to the hosted domain, IP1 to IP4. As a result, when user query a set of hosted domains, the resolver will redirect the legitimate traffic toward 4 candidate authoritative servers. So far, so good. Now, we assume the attacker wants to attack a single NS record, NS1. The attacker's configuration is stayed here. The NS record of attacker's domain is set as NS2. Note that the attacker's domain is not hosted on the target authoritative server. Then the attacker requests the resolver to resolve his domain. According to the configuration of the attacker's domain, the recursive resolver turns to query NS2. However, since the domain is not hosted on the target's nameserver, the nameserver slightly drops the request of the resolver. Consequently, the recursive resolver records the failure status of NS2 and lower its priority. The status of nameserver is shared across all domains, including both the attacker's domain and the hosted domains. As a result, when billion users query the hosted domains, the resolver avoids selecting NS2 and forward the query to NS1. The load balancing of authoritative server is disrupted. Also, the attacker can perform another variant and target a single IP address of authoritative servers. In this case, we assume IP1 is the victim, and the nameserver of attacker's domain is finally pointed to IP2 to IP4. After receiving attacker's query, the resolver turns to query IP2, 3, and 4. The nameserver drops the request of the resolver, and the resolver records the failure of IP2 to IP4. When billion user query the hosted domain, the resolver forward the query to IP1. The load balancing of authoritative server is disrupted. Now, let's move to the evaluation of this attack. We first evaluate exploitable hosted domain, authoritative servers, and server providers. To this end, we conduct a large-scale measurement. We select the top 1 million second-rank FQDN and the top Q SLD as targets. Then we request the NS records at the parent zone for each domain, along with the IP address. Further, we mark a nameserver as vulnerable when it satisfies 2 conditions. It ignores queries for a domain that is not hosted and responds to its hosted domain. Our measurement results show that about 23% of the top FQDN and about 4% of the top SLD can be exploited by this abilities. Zooming in the top 100 domains, the population of vulnerable FQDN as SLD increased to 29% and 11% respectively. Such vulnerable domains are related to popular applications. For example, the API for a mobile operating system, short form video applications, and e-commerce. Our results also show that in the top FQDNs, around 12 of authoritative servers were exploitable. These abilities can also impact the popular services provider. For example, DNS-Point, a popular provider affected by these abilities, is hosting a number of popular sites, including around 6% of top FQDN and about 1% of top SLD. We evaluate the amplification factor of these abilities, which means that the multiplier of the traffic load on victim caused by legitimate traffic. While targeting an IP address, the average AF is around 8 times and 7 times for the top FQDN and the SLD. The maximum AF is 32 times and 46 times respectively. Interestingly, we find that domain requiring high availability suffer a great amplification impact since they are assigned more nameserver for load balancing. For example, the AFs reach 46 times for a vulnerable SLD owned by a technology company. We also evaluate the exploitable target from the sign of resolver. Here is our methodology. We select the recent version of 5 min-trings recursive DNS software. Then we conduct a white box analysis for open source software. We perform code reviewing and dynamic debugging for them. Further, we evaluate the impact of these abilities through simulation. For open source software, we extract the essential code and execute it in a simulated environment. For closed source software, we run the whole operating system, the Microsoft Windows Microsoft DNS system in a simulated environment. Our results show that 3 of the 5 analyzed software are vulnerable. Such vulnerable software is enjoying high market share. Unfortunately, we also observe that the efficiency of these abilities is quite high under different conditions. For example, during the simulation, we found that on average, Band9 sent about 6,000 legitimate queries to the target nameserver after receiving only 1 query from the attacker. We further conduct an extensive measurement to confront how these abilities affect real-world resolvers. We select about 40,000 stable resolvers and include 14 well-known public DNS recursive services as our targets. Then we act as the attacker and the billion client to send queries to the target resolver. We establish a set of vulnerable nameserver to receive the request of tested resolver. And we configure our domains as attackers and the victims domain as for ethical consideration. We found that about 38% of the tested open resolver are vulnerable. They are distributed in many countries, cities, and AS. The results indicate that the vulnerable resolver serves many users whose DNS traffic can be diverted by these abilities. We also observed that 10 of 14 popular public recursive services are vulnerable, including Cloudflare, OneDNS, and Quant9. Here is the discussion and the conclusion about this study. We conduct the rule reason causing these abilities. From the view of the authoritative server, we discussed these issues with affected hosted servers. They confirmed that dropping DNS queries for non-authoritative domains is adopted as a defense mechanism to protect against DNS amplification attack. From the view of the recursive resolver, it decreased the priority of a nameserver when the query is timeout, and share the status of nameserver across all domains to improve the efficiency of domain resolution. To mitigate the security issues, we believe the authoritative server should take responsibility since their strategy violates the DNS specification. Obviously, 8906 said that failing to respond at all is always incorrect. We suggest an accurate response for non-authoritative domain that follows the DNS standards, returning refused with an eDNS error code. In the case that some nameservers do not support eDNS, we suggest returning refused instead of other misstanding errors. This response do not introduce other DOS attack vectors. After disclosure, Tsinghua, Amazon, and the TSS-NS had taken action to fix this issue. We also believe adjusting the recursive software is far more efficient for fixing this issue, since these software are installed on most of the affected resolver. We recommend address these issues by adopting the strategy of not resolver. Although not share the status of nameservers across all domains. However, it tries other candidates with certain probability and restore the status of a field nameserver once it responds successfully. After disclosure, all vendors of vulnerable software acknowledge our findings, but they insist that authoritative servers should fix this issue. Here is the conclusion of this study. First, we uncovered a vulnerability that targets the load balancing mechanisms of a kind of non-compliant authoritative DNS servers. Then we evaluate the real-world impact of our proposed attack. Finally, we disclose issues to vendors with mitigations option. Tsinghua and Amazon have taken action to fix it. Here is the reference. Thank you for your interest in my presentation. Wish you had a nice day.
Thank you for the talk. It was so good that it actually answered a couple of questions in slides while their questions were popping up. So now we are left with the questions in the room. Shumon, please.
Yeah, Shumon Huck, Salesforce. Thank you. Excellent presentation. So you mentioned you identified vulnerable recursive server implementations, but for authoritative servers, the ones that don't follow 8906 and are silent, you only mentioned X% of Tranco or blah, blah, blah. Have you identified the list of authoritative DNS server implementations, either open source software or DNS implementations that do not follow this recommendation?
Thank you for your question. In fact, it is we believe it is difficult to identify the exact implementation of authoritative server.
Yeah.
Despite there are some kind of such as child's queries or NSID, but for some protective purpose, they may not provide the true version of the DNS servers they used. So we did not conduct such experiments, but we established our servers as vulnerable name server. Establish our attacking domains and victim domains to text if they were vulnerable through a black box measurement.
Okay, great. Yeah, so I understand there are some challenges, but there are also some ways you could determine some of this stuff. Like, so if you have open source software, you could set up tests, you could do it yourself, right? And you can also set up domains on managed DNS providers and do some tests that way too.
Do you mean that we step up the name server? Oh, yes, the mainstream authoritative DNS servers did not adopt this non-compliant strategy by default.
Okay.
This is because the hosting provider or the owner of vulnerable name server, their operator configure this in particular.
Okay, great. Thank you.
Ralph, welcome. Just to add an anecdote to that, there are cases where authoritative DNS servers use some eBPF or stuff where when they're under attack for one domain, they just kind of answer nothing for that and still answer all the others. Hence, I'm coming to the point. It will, I mean, if you are not sharing the name server state per IP, but instead per domain and IP, you're not vulnerable as a recursor to this attack, right?
Excuse me.
When you are, I mean, you said the problem that was a sharing of the state of the authoritative within the recursor based on the IP.
Yes.
If you would use the name and the IP, this attack would not work.
Do you mention
the domain? So
I don't really understand this
question.
Do you mention this is a kind of mitigation option?
Yes.
No. As I present before, there are two variants of this billions attack. The attack can also target a single NS record. And the NS records provide the domains of the authoritative.
No, I'm not meaning the domain of the NS record. I mean the domain of the domain you are trying to ask for. We can.
Do you mention that the recursive resolver should record the status of name server for each domain?
Correct.
Yes. Steadily. In fact, this is the algorithm take by Unbound. They did this, but we did not recommend because we think there may be a lot of algorithm adjustment to the such as band 9 their implementation. So we recommended the implementation of not resolver because the not resolver also share the status of name servers across all domains, but it add a probability to try other candidates. So this may then make this billions attack cannot affect them. We believe this is a simple way to address this.
But the other way still works.
Yes, both ways works.
Okay, thanks.
Works.
Ed Lewis, I can. So I've been listening to this and trying to understand exactly what you're addressing. The attack is started by a query, which some people call it's a lame server situation. The lame server is an old term, and it means you're asking the server for something it knows nothing about, right? And the lame servers used to respond a certain way. We've changed that to reduce the application of responses. So, and I guess this is kind of a comment and not really a question, but in your presentation, you never referred to the word lame server or lame situation, which might make this clearer to many people who've been around for a long time. They understand now why, like the authoritative servers are supposed to respond to queries that they know nothing about, they're lame for in a certain way. But if you're finding servers that are not responding at all, I can understand where that can start causing some issues down the line. I think that's important. If you're identifying servers that don't respond, they're probably not the ones we normally think of when they handle this lame server situation. The question that Ralph was asking was about now the recursive side, how recursives see this. And I'm not that well versed in recursive servers to know what's going on these days, but I would have the same reaction he did, that if the recursive server is associating stats with an IP address, it's of course going to be misled by the lame queries knocking out all the others. But I would be surprised if many recursive servers do a blanket labeling that way. If it is, it's interesting to know that. But, and as Ralph was saying too, if you tag the IP address with what I'm asking for, then you wouldn't see this. But this is me just trying to understand the presentation more than a question, to be honest.
Thank you for your comments.